So I'm going to begin by continuing talking a little bit more about leaf spaces, and that'll bring me to the end of lecture 1, and then I'll start lecture 2. So remember, we're working under the assumption that when I talk about a three-manifold, it's going to be at least compact, connected, oriented, and smooth. And when I talk about a foliation, I'm going to mean a codimension 1, typically co-oriented foliation of such three manifolds. And we were talking a little bit at the end of last time about this theorem due to Palmyra, which tells us that if we look at the lift, so if we begin with our codimension 1 foliation of three manifold M, and we pass to the lifts, so M tilde, the universal cover of M, and F tilde, the lift of the foliation to this universal cover, then Palmyra tells us that this is homeomorphic to R2 cross R. So in particular, the universal cover is R3, and the foliation looks like a nice foliation of R2. So a nice codimension 1 foliation of R2. So nice in particular means that the leaves are properly embedded Rs. Cross R. So if you want to visualize any F tilde, you can just visualize any nice foliation of R2. So that's a much easier dimension to think in. And then go cross R. So we can completely visualize what's going on. And key in the proof was that if we look at the leaf space of F tilde, this is a simply connected, not necessarily housed off one manifold. Okay, so we have this setup, and I just wanted to give another example. So I'm going to think about giving as an exercise computing the leaf space of the following setup. So M is just going to be closed surface cross S1. So F2 is closed oriented surface. And then I'm going to give you and let's see, let's fix the genus. So let's say I've got a hyperbolic genus. Well, hyperbolic in this particular example, I'm going to think genus 2. So in this case, I know what M tilde is, and I have a very nice picture of what F tilde is. I've just got H2 cross R or R3. And I want you to think about, I'm going to give you a particular geodesic lamination of my surface. So my surface isn't Euler characteristic 0, so it doesn't admit a codimension 1 foliation, but it does admit as close as possible object to this. So I'm going to think about lambda is and maybe I shouldn't use lambda because lambda has special meaning. I know foliation, phi for foliation. So phi is going to be, or L. Oh well, doesn't matter. So this is going to be a geodesic lamination in F2 that has exactly 2 complementary regions, each of which is homeomorphic to a full cusped disk. So I can think about that as the way in which it's embedded in my surface. So as I go out to infinity, these are approaching each other, these two leaves are approaching each other exponentially quickly. Or I could think about this as a missing boundary D2, missing full points. And I'm going to express the particular example I'm thinking about using a train track. So this is an example of something which is known as a train track. It's co-oriented, as long as I copied correctly from my notes. So if I think about giving myself a co-orientation, I've got this. So the idea is, so a train track is just a space that locally either looks like a manifold, or I can have these train track-like places where I've got double points. And I talk about a lamination being carried by the train track if it can be isotoped so that it lies in a little nice neighborhood of my train track. So I've given a train track, so a train track is equal to a space modeled by, well, it's either a one manifold, so I've got regular points, or I've got double points isolated. And if I start with the train track, I've got an associated I-fibered neighborhood. So I can think about this regular point. I just think about taking a regular neighborhood and choosing some I-fibering. Here I have a picture like this. And I've got an I-fibering. And I say that a lamination is carried by a train track if it can be isotoped so that all of the leaves lie in this nice neighborhood and the leaves are everywhere transverse to the I-fibering. So I can think about geodesic laminations are in general complicated, but they can be carried by nice train tracks of the sort that I just drew. And if you already know about train tracks, you might know that geodesic laminations correspond to, or can be described corresponding to choosing measures on your train track, choosing little weights. If you haven't heard anything about that, it really doesn't matter. But if I look at this train track, I can see that I've got two complementary regions that look like 4 cusp disks. And I'll just say that there's a way of making precise everything that I just said. So if I have a geodesic lamination, I can choose one that has exactly 2 complementary regions, each one homeomorphic to a disk with boundary S1 minus 4 points. And so now what I want to do is take this lamination, and what I'm really interested in is a foliation of M. So we're going to think about taking, let's say it's lambda is just going to be this phi cross 0, 1. And here I have, I'm just going by the identity. So x1 is going to be glued to x0. We're just gluing our F2 cross, I'm thinking about I've got my F2 cross I, top's glued to the bottom by the identity. So I've got this lamination in a slice, and I just go, I don't know why I did it this way, because of something I'm doing later. I should have just written this. So I can think about suspending the lamination that I have in my surface. So I can think about taking that lamination and going cross S1. That's going to give me, again, not yet a foliation because I haven't filled up my manifold, but I can fill up my manifold. And I'm going to think about my lambda as obtained by what's commonly known as stacking chairs in the complementary regions. So what do we have? We've got complementary regions that look like across S1. So they look like solid tori with 4 cusps. So you can think about that corresponding to 4 sutures. So I've got 2 regions of this sort. And let me just introduce some color. I can think about, maybe this is my red leaf, and I'll just leave the other leaf as white. And let's just focus on one of these at a time. I'm going to think about taking disks. In a sense, this is very similar to the game we were playing when we were constructing the RABE component. You think about taking meridian disks that foliate the solid torus, except I want to have pieces of my disk now spiral in and have in their limit set the boundary of this solid torus. So I'm going to think about maybe so this shouldn't be thought of as being the end of my saddle. This is extending up up to infinity. This piece is going down to infinity. Piece behind is going down to infinity. So I've got these non-compact chairs, and I'm thinking that as I head up in this direction, I'm limiting on the red. And as I head down in this direction, maybe I should use color. I've got the blue and the blue. I'm limiting on the blue and the blue right here. So if I think about, I began with something transversely oriented. So let me do the transverse orientations. Maybe I chose to do this. So you can notice that automatically, since I'm transversely oriented, this arrow is right here. So once I've chosen red, I've chosen blue, which decides red, which decides blue again. So I need an even number of cusps for this game to work, but it's going to work whenever I have an even number of cusps. And then we just think about filling in the solid torus with an S1's worth of these leaves. And we're going to see that if we take the closure of any one of these leaves, we're going to get the leaf itself together with this leaf, this leaf, this leaf, and this leaf in my foliation. So this is a game you can always play if you've got if you've partially filled up your manifold with something that's trying to be a foliation, and you end up with complementary regions which are just solid tori with an even number of cusps. So you can think of those as taut solid tori if you prefer to think in that way. Then you can always extend to a foliation. So if the complementary regions equal solid tori, so that the meridian disk has even intersection number, so even and not equal to 0 intersection number with the cusps or with the sutures, then you can fill in the region with stacked chairs. So, I need to be able to alternate red, blue, red, blue, red, blue. So I need an even number. But as long as I have that, I can play this game. Okay, so now let me give you an exercise. And that's to compute the leaf space of the lift of this foliation. So it's very easy in this example to move from M to M tilde and to get a very concrete picture of your foliation. And so it's not too bad to compute its leaf space. And partly what I want this example to begin emphasizing is that this is fine if I want to say this is how I can visualize any lift of a foliation, and it's a very, very nice way to compute the simply connected, not necessarily Hausdorff-1 manifold, because I just look at my lamination of the plane and I can see what my leaf space is going to be. But given a foliation and its lift upstairs, it's I've got lots and lots of choices here, and it can be tricky to see because of the interestingness of having a missing boundary B3. So here are two exercises. So one is show that if I have R2 and I've got it foliated by, I've got some number of vertical lines, let's say at every integer point, and these are filled up by these parabola-like things. And let's say here I choose to fill things up so that the parabolite things are all pointing up, but this is not homeomorphic to R2, where these things alternate. So if I'm in 2 dimensions, those things are not homeomorphic. But if I give myself an extra dimension and try to lift this board up, so if I have R3 and I look at this thing cross R, then that is homeomorphic to R3, this thing cross R. So there are interesting things that happen. You've got room when you've got 3 dimensions to move your picture. And so then the final exercise is to, what's lambda for this particular example? Oh, do you have a question? I would love a question. Go for it.
So all the leaves are non-compact, so there's only one leaf type.
All the leaves are non-compact.
This exercise.
Oh, yes. Right. So they're just R's. Well, actually, no, I have to be a little bit careful. So I've got R's cross S1, so I've got annuli. And then I've got discs. I've got R2s. Okay, so mostly the point of this example is that very, very quickly, even though you have this really, really nice picture, life gets complicated. And generically, in some sense, you should think about, or probably you should think about leaf spaces generically being not Hausdorff. So the case that you have Hausdorff is very special, which makes the left orderability, if and only if there exists a co-oriented taut foliation, much more interesting than it would otherwise be. But it is really nice. You've got this 3-manifold, you want to understand it, and you've got this decomposition of your manifold into surfaces, and it's even better. You've got sort of transversely, you've just got this 1-dimensional manifold, at least when you move to the universal cover. And so sometimes let's see, I should over here somewhere, I forget if I mentioned yesterday, you've got your universal cover, it's acting on M tilde, and that action gives you your action on your leaf space. So you know that if you have a Rabelais foliation, And let's do CTF from now on. So if I have a CTF, then I know that I have a non-trivial action on this simply connected one manifold, so LF tilde, by orientation preserving homeomorphisms. And by here, non-trivial, I'm meaning that there isn't a generalized global fixed point. So there doesn't exist a, let me write generalized fixed point, and then if you let me get away with it, I won't write down what that means. But if I had a Hausdorff space, I would mean that I had a non-trivial action if there was a, well, it would just in this case be really boring because it's OR, and so you've got various notions of non-trivial and they're all equivalent. But what I mean by non-trivial here is that there isn't a fixed point, there isn't morally a fixed point, but it might be that my fixed point is an equivalence class of non-separated points. So you're saying that there isn't either a point that's fixed or an equivalence class of non-separated points. That's fixed. And sometimes you can use this to rule out the existence of foliations. So sometimes you can show there doesn't exist a non-trivial action on a simply connected one manifold, always assuming we are not assuming Hausdorff here, to tell me that there does not exist a CDF. And I guess it's much easier than, if you're in a world in which you are, well, now with modern techniques, if you're in a world where you know that you're not in L space, you've got problems in proving existence or non-existence. And this is a technique that's, in general, if it works, going to be easier than just trying to work directly with the foliations and the non-compact leaves. So the non-compactness makes sort of hands-on arguments with your foliation of proving non-existence of a foliation very difficult. And of course, going back to the sequence of conjectures that Cameron talked a lot about, we can ask ourselves, well, so is it true that if pi 1 of m, so if there exists a non-trivial pi 1 of m action on a simply connected one manifold, is it true that you're going to have a non-trivial action on R? Okay, so I think that's all I wanted to say about leaf spaces for now. Are there any questions? This being the end of lecture 1. Okay. Okay, so this is, I can think about, this is one sort of nice construction technique, stacking chairs. So we'll come back to talking about stacking chairs. In the time that remains, I want to begin by talking a little bit about minimal sets of foliations and using them to show examples of obstructions to having your foliation be C2. And then I also wanted to talk about a very useful operation on foliations called Dangerois blow-up. And then if we've got time, I'd like to use those to give examples, or to build some examples. Okay, so I want to start thinking about minimal sets of foliations. And actually, first let me just make an observation. So we have a foliation of a compact manifold. And the generic situation is that I've got lots, maybe only non-compact leaves. So I've got F, a foliation of M. And I can think about if L is compact, then I've got that L closure is just L. But if L is non-compact, then L closure is going to properly contain L. Now we want to think about sets that look like L closure and don't properly contain any other leaf closure things. So we have this definition. So lambda, so a minimal set lambda of a foliation F is a minimal F saturated closed subset of M. So F saturated just means that if my subset has non-empty intersection with a leaf, it's going to contain the leaf. So if leaf intersection gamma is non-empty, then that implies, I don't know what I'm calling this leaf, let's say F, then that implies that F is contained in lambda. And minimal means minimal with respect to F saturated closed, I guess I should rule out empty subset of my manifold. So a minimal set of a foliation is just a minimal F saturated closed non-empty subset. So it's minimal with respect to these adjectives. And equivalently, lambda is equal to L closure for some leaf L, and not, and let's see, L prime contained in lambda implies that L prime closure is equal to lambda. So there isn't a smaller leaf closure, smaller non-empty leaf closure that's contained in my set. And I can notice that in particular this is telling me that L prime, that any leaf L in lambda implies that L is dense in lambda. Oh, and I've erased my example. So an exercise, I guess, since I don't have the picture anymore, is to think about the minimal set of my foliation in that example, and it's not going to include those stacked chairs. And an elementary topology exercise is that if we've got lambda, a minimal set, then it satisfies one of the following. So exactly one of the following. So one possibility is that lambda is a compact set. So compact set is its own closure, so it's certainly not going to contain a smaller such set. Another possibility is that lambda is the entire foliation, so lambda is m. And the third possibility is it's neither of the first two. It's what's called an exceptional minimal set. And in this case, if you have a transversal, so if tau is a transversal to f, and I'm just thinking a little segment, a little closed interval to f, such that the interior has non-empty intersection with my minimal set, then this intersection is going to be a Cantor set. So you've got this closed F-saturated thing, and you're just thinking, well, what are closed subsets of the interval? So one thing we can ask ourselves is, well, if I give you a foliation, how many minimal sets can I see? And if we restricted attention to, well, how many of this, well, easiest case, I guess, is, how many of these can we see? Well, one. If we restricted attention to minimal sets of this sort, we're just asking ourselves, well, how many compact leaf. So we're asking ourselves, well, how many compact surfaces can we see? And we know that, well, we could play some sort of Hawken game, triangulate our manifold, use Hawken normal form, and say that, up to isotopy, we've only got finitely many isotopy classes of compact surface. So we can show, so Hawken normal form, so triangulation plus Hawken normal form implies finitely many isotopy classes. So there might be infinitely many minimal sets of this sort, but they're going to be related to each other in this very boring way. And more subtle is to think about exceptional sets of this sort. And there is a result of Gabai's that tells you again that you can think about triangulation. So there exists a triangulation so that f is in Hawken normal form. Or actually, so that lambda, I need to be a little bit careful. Let's do it this way. Lambda is in Hawken normal form. And so again, same game. There are finitely many. This time, really are. You can't have isotopic Cantor exceptional minimal sets. So finitely many exceptional minimal sets. There might be none. It could be that the minimal set is the foliation itself. But if you have exceptional minimal sets, there can be only finitely many. Okay, so now we're set up to describe a nice example, well, at least to state a nice theorem to Donjois. And so he proved that if you have a C2, so we're 1D lower, thinking in the torus, we need genus 1 so that we actually have a foliation. And if we think about a C2 codimension 1 foliation of T2, he proved that F has no exceptional minimal sets. So in a few minutes, we're going to describe this operation called Danjois blowup and see that you can find foliations of T2 that do have exceptional minimal sets, and so by Danjois, they're going to necessarily not be C2. And if we go up a dimension, so we're in the dimension we care about, which is 3 manifolds, and suppose you have a C2 foliation of M3, then you know that, well, I'm going to throw some jargon at you and then just tell you what we care about. So, exceptional minimal sets have what are called resilient leaves. For these lectures, all we care about is that this means that there are leaves with contracting holonomy. So each exceptional minimal set has a leaf with contracting holonomy. And I'm going to draw a picture to say what that means. So Saxtetter is telling us that if we have C2 smoothness, then we have this particular property of exceptional minimal sets. So if you stare in and you're looking at particular foliation and you see that exceptional minimal sets do not satisfy this property, you know you're not C2. And so here's the story. I think about in there's going to be a leaf. Let's call it L. There's going to be a simple closed curve in that leaf. Let's call that gamma. We're then going to think about choosing a little vertical annulus with core gamma. So we're going to think about choosing, locally we know that we just have little foliation charts. So it makes sense to find an annulus, let's call it A, and A is everywhere transverse to F. And if I look at how the leaves of L intersect this annulus, well, I'm going to see the gamma, but then elsewhere I'm going to see leaves just entering my annulus and spiraling around that curve. And they're going to spiral in the same direction when I enter from below and when I enter from above. So if I'm a C2 foliation, I look at my exceptional minimal set, I can't find such a gamma, I know that I'm not going to be C2. So again, I've got a topological obstruction to having C2, and a lot of the constructions of foliations that use branch surfaces, for those who are familiar with that, end up failing this Saxtetter condition. Okay, so there's an operation that we do over and over and again when constructing foliations, and it's called Danjois blowup. Maybe it should be called Danjois d'Hippolyte blowup. So Danjois can be thought of being defined when we're in the torus case, and then Dipolito generalized to codimension 1 foliations in arbitrary dimension manifolds. But let's carefully go through the Donjois description. So I remember as a grad student being in the room with my advisor, Alan Hatcher, was giving a talk and talking about Donjois blow-up, and John Hubbard was in the room, and he got incredibly unhappy with Donjois blow-up. Because you have to be careful in how you talk about it. So I do want to just take the time to go through it carefully and show that, at least in dimension, codimension 1 and dimension 2, it's very easy to make everything really, really precise. And then we're going to be actually doing Donjois blow-up. You can think about it as really having done it on a little one-dimensional interval. And if you move up to arbitrary dimension but codimension 1, you're just going to have your little foliations. And you can think, as we proceed in what I'm going to just describe right now, you could do the same thing sort of chart by chart. And you would have to be careful that as you move between charts, everything agrees at the end, but that's pretty easy to do. Okay, so let's begin by thinking about that example we had last time of a foliation of the torus by irrational sloped lines. So remember, we have this little usual covering ST goes to e to the 2 pi is, e to the 2 pi it, and we end up, we can take a leaf here, say, look at its embedding downstairs, and we end up with pi of L closure is equal to a whole manifold. Or we can think about pi of L closure is just equal to pi of the union of all the lines upstairs. So let's say Ly, where y is just my y-intercept. Okay, so this is just an example of a foliation of the torus. And I want to now re-describe that foliation as a suspension of S1. So I could think about taking a cylinder. Let me draw my cylinder like this. And I can think about just foliating the cylinder by intervals. So I've got my cylinder is just whichever direction I want to move in. So let's say S1 cross 0, 1. And I'm going to think about foliated by the Z cross 0, 1s. So I've got a foliation by intervals of this guy. And then I can think about choosing my map, F, just take Z to, let's say, e to the I pi 2 pi I theta Z, where this is an irrational rotation. And as long as I choose irrational rotations to match up, I've just got another description of the foliation of T2 that we had up above. And what I want to do next is Donjois blow up this foliation. So I guess I didn't give it a name. Let me give it the name phi for foliation. Or actually not. Let's call it F, even though I'm one-dimensional. So we have this foliation, and now we're just going to say, okay, let's look at an orbit Z to the n of my homeomorphism F, or equivalently L intersect my S1 cross, 0 is identified with 1. Where L is any leaf of F. So I can focus on the leaf L, or I can focus on its intersection with this circle after I've done my gluing. So maybe I have a Zn, I have a Zn plus 1, etc. And then we're going to blow up, we've got countable and many points Zn, and we're going to blow them up to an interval Jn, and we're going to do this so that the sum of the Jn lengths is finite. So we're going to replace S1 by a new S1, which is a blow up of the old one, by replacing each Zn with a little closed interval Jn, so that the length of the Jn is finite. So wherever we had a little Zn, we've now replaced with a Jn, and maybe I can think about Zn plus, Zn minus. So I've replaced, let's say here was a Zn, here was a Zn plus 1. I've sort of replaced this by, I've added in an interval. I had the leaf that I had here, I had the leaf that I had here, and I've maybe got a Zn plus 1, maybe that's a tiny, teeny, little interval. And I've got this. So I've got this new S1, so I can think about new S1 cross I. And if something wasn't blown up, I just have the interval as before. If something was blown up, then I'm going to have an interval's worth of leaves. So I'm going to have my new S1 cross I again. Foliated by Z cross I, Z in the new S1. And I'm going to get an F prime, which is obtained by doing the gluing with, well, we had F before, now we've got G. And let's just think about describing G. If I had a point a point cross 0 and a point cross 1 that wasn't one of the Zn's, I'm just going to have my F be defined as, my G be defined to agree with F. And then on these little blown up intervals, I'm just going to extend linearly. So we end up with this new foliation, and F prime is called the Dangeroux blow up of F. And we can think about, if we think about the new S1 prime cross S1, here's my new torus, and I think about looking only at the original leaves, so the leaves that do not cross the interiors of those open intervals Jn. I see that I've got a Cantor set transversal. So the original leaves have Cantor set, or meet transversals in Cantor set. So meet, let's say, the new S1 cross 0 in a Cantor set. So if I think about the union of the original leaves, I have a minimal set, and it's going to be an exceptional minimal set. So a union of the original leaves is going to be an exceptional minimal set. So sorry, that was probably too quick, but the idea is that I have this foliation of my torus by non-compact lines R. I can focus in on one of those leaves and I can blow it up. I can replace L by L cross I. And I must think about the fact that as I go out to infinity, things must be decreasing quickly enough so that the space I've created has length, finite length. But this is a nice operation that I can do. And in general, if I have a leaf, a codimension 1 leaf in a 3-manifold, I can play the same game. I can think about taking that leaf and replacing the leaf by L cross I. So I can think about Donjois blow up. I have an L, a leaf of my foliation. Oh, and this can't be seen by many. So in general, I have F, a foliation of M3, or in general, codimension 1 in Mn, and I have a leaf L. I can modify F goes to F prime. So L is replaced by an I's worth of copies of L, and everywhere else the foliation just looks the same, has the same leaves. And this is, oh no, this is terrible. I have too many consonants and I didn't. Oh dear. Okay, I'm apologizing to all the Italians in the room. If you could yell, oh, I know. Cameron knows the spelling. How do I spell Dippolito?
I think I suspect you're right.
Okay, Dippolito.
No.
Okay. So sorry. So yeah, so Dippolito, my understanding is he had this one beautiful paper and then he was in a horrible car accident. And that was the end of the math career. There's one important difference when you move up a dimension, though, and that's that when you have L in general a surface with genus, you can you don't have to just replace by a product. You can replace by leaves that do interesting things. So you can replace by leaves which are covers of the L. And you can take advantage of that. So we have, so in general, so in dimension, so greater than or equal to 3, you can insert, so L can go to more interesting foliation of L cross I. Okay, so this is a really important operation on foliations, this notion of Donjois blow up. And what I want to, in 4 minutes, I have nothing really that I can say, but I'll say one thing. So Liam pointed out that the examples we've looked at so far, the leaves are really, really boring. So far, if you think about the examples I've described to you, either we have compact leaves or we have non-compact. I reinterpret what you said, and it was a very good observation. So we have, non-compact annuli. We have non-compact R2s, but in general, there's a result due to Cantwell and Conlin, which tells you that even if you restrict to smooth foliations, the infinity foliations, any leaf can can be realized, any surface, including any non-compact surface, can be realized as the leaf of a smooth foliation. So we have this theorem, and Conlon from 1985, that every surface, so every, let's say within the oriented world, so every oriented surface, not necessarily compact, can be realized as the leaf of some C infinity foliation. And we're out of time. But what I was hoping to do was to give you a hint at, useful ways you can visualize foliations, knowing, here's an example of the fact that they can be much more complicated than the ones we've looked at so far, and also go back and say a little bit about Eliashberg-Thurston in the case that we're not smooth. And clearly I won't really be able to do both. So if you have a preference, let me know sometime before tomorrow. That would be good. Thanks.